try to unite all the periodic trends through some sort of physical intuition that I can give you. And it is not going to be a series of rules for you to remember, although eventually that can be the takeaway that you get. And instead, it's going to be you thinking about the energy of an electron and how attracted it is to the nucleus, how attractive it finds the nucleus. And the more attracted the electron is to the nucleus, the harder it is to pry that electron away. So here's the periodic table. We're going to determine different trends. So like here's a hydrogen atom. It has an atomic number of 1, so it has 1 proton in the nucleus. And if it's neutral hydrogen, then it has 1 electron. Here we have helium. It has like 2 electrons and 2 protons in the nucleus. So with that in mind, we could ask this question: which is going to be more attracted to the nucleus of these two systems? Is the 1 electron in hydrogen going to be more attracted to the nucleus of hydrogen, or is an electron in helium going to be more attracted to like the nucleus of helium? We could even go crazier and say like something like potassium. So like there's 19 electrons surrounding a nucleus that has 19 protons in potassium. Is one of those potassium electrons, like one of the electrons that's in like the outermost filled or occupied orbital of potassium, is that outer electron going to be more attracted to the nucleus of potassium than an electron in one of the outermost orbitals of krypton is attracted to its nucleus that has 36 protons in it? So to make a crude analogy, we could talk about like a sports bar. So you could have, a sports bar with, 3 TVs. And you could have another sports bar with, let's say, 10 TVs. Okay, so if this was a sports bar that had 3 TVs versus a sports bar that had 10 TVs, and you were just like one person and these are both empty, which one is going to have more attraction to you? Probably the 10. I mean, like they might have something on that you want to watch. It's not the most perfect analogy, but let's go with it, okay? So like they might have a particular game on that you want to watch. They might have a nicer set of TVs. I don't know. So if there's just 1 electron picking between 2 different nuclei to be around, it would definitely pick the one that has more protons in it, because electrons have a negative charge and protons have a positive charge. And if you're the electron, right, if you're like this electron and you're trying to pick, right, like which one to go to, you're going to pick the one that has the higher positive charge, because you have a 1- charge. And these things this has a 3+ charge, and this has a 10+ charge. So you're going to be more attracted to the higher positive charge. So 1 electron around a 3-proton nucleus is going to be less attracted to it than a single electron around a 10-proton nucleus. Okay, what if it was a 1 electron, or let's go back to our sports analogy. What if it was 1 patron deciding between a 3 TV sports bar and a 10 TV sports bar that has 7 people already in it? And these are not sociable people. These are like electrons, so they repel each other. And they also don't like, sharing, like flipping between channels. They hog TVs. So which one would you rather go to? The sports bar that has 10 TVs and 7 people in it, or the sports bar that has 3 TVs and no people in it? So we got one person saying 3 TVs. You might also say, okay, 10 TVs with 7 people, because that means that there's 3 spare TVs, plus the other TVs might have what you want on them. Something like that. This is a hard one, though, right? It's not as easy as the previous question. The previous question was super easy, right? It's like 10 available TVs versus 3, duh. Once we get to this, it's like, well, there's another consideration. We might want to consider free TVs as opposed to just existing TVs. And now it's 3 versus 3, and I don't know what to do. And it gets even more confusing because you might have like 8 people or 9 people, and then you have to sit there and go, okay, is 1 available TV and 8 partially taken TVs, is that, or 9 partially taken TVs, is that actually more attractive than 3 completely free TVs? I don't know the answer to that. That depends on the sports bar. It's too hard. That's the kind of consideration you need to have when you're thinking about periodic trends. You have to think about how much the outermost electron might be attracted to that nucleus, given that there are already electrons surrounding the nucleus and that the electron is negatively, it repels. It's negatively charged and the other electron is negatively charged. So they repel each other. And there's something worse yet. So if you're an electron, I'm going to do everything with s orbitals because they're easier to draw. It's not really true, but we're going to go with it. Remember, those p orbitals, when you start putting them together, they start looking kind of like, as a whole, they kind of look like a fortress thing that like surrounds the crap out of the nucleus anyway. So, spheres aren't the worst thing to draw. They're not spherical individually, but like when you start putting them together, they start, looking kind of packed in pretty well, almost like a sphere. So let's say I have a nucleus, and this is not to scale, of course, but I need to draw things on it. This has to be really big. So that's the nucleus. So let's pretend that's the nucleus. That potato-looking thing is the nucleus. And then this would be a 2s orbital, and this would be a 1s orbital. Okay, so if there's 1 electron only in this 1s orbital, it would see the nucleus, and this would be a 3 plus charge in the nucleus, because 3 protons, right? And one electron would see the nucleus and be like, okay, I see a 3 plus charge. That's a lot of attraction between a 3 plus thing and a 1 minus thing. So that's pretty good. If there were 2 electrons in the 1s orbital, sometimes, because it's a probability function, sometimes one electron's going to be closer than the other electron, right? Like sometimes you might have a situation where there's like 3 proton. I'm not trying to say 3p. It should be 3 proton. So I should make this uppercase so it's not like ambiguity here. So 3 protons in the nucleus. Sometimes an electron might be here, and another electron might be over here. So that has a 1 minus charge, and this has a 3 plus charge. If this is the case, this electron that's outside of both the closer 1s electron and the nucleus would be shielded by this electron. It wouldn't see the full 3 plus charge of the nucleus. It would see what's closer to a 2 plus charge. So it's been shielded by this other electron. It only sees 2 plus overall charge. So this phenomenon is called shielding. And what it means is that when I add an extra electron to the system, it's not going to be as attracted to the nucleus as that first electron was. And if you had an electron in the 2s orbital, so that there were 3 electrons total, this electron might see, there we go, might actually see a inner core for the system that has a 1 plus charge, because there are now 2 electrons that might be in between it and the nucleus. And then in this scenario, it would only see a 1 plus charge. Pretty crazy, right? It's been shielded by both of those 1s electrons. Now, it doesn't always work this way. Sometimes these electrons might not be exactly in between this electron that's outermost and this nucleus. They could be on the other side. Or sometimes this electron, even though it might be in a larger orbital, just because it's in this 2s orbital doesn't mean sometimes it won't be inside the 1s orbital. It could be. The probability function for this thing looks like a pea soup or something. I mean, sometimes it's going to be inside the 1s. But as you get higher and higher energy, they tend to be bigger and bigger orbitals, and they tend to spend more and more of their time outside of the more inner orbitals. So the idea that these things are going to be outside more often than these things are inside, that's true. And that they do get shielded, at least partially, by these inner more electrons. So the lower energy electrons will tend to shield the higher energy electrons, who have a large portion of their time being outside those inner more electrons. And this really is very confusing to me, because it means I can't do a lot of things. So I can tell you some things, like we can come to some conclusions together. Like if I have a system that has 3 protons in it, every time I add an additional electron, that additional electron is going to be less attracted to the nucleus than the previous electrons were, right? So like, remember when we just had 1 electron? Wow, that electron was super attracted to the nucleus. Way more than when we had 2 electrons, because now there's an electron that might be getting shielded by the other electron, right? And if I add another electron, that one's going to be even less attracted to the nucleus because it's shielded by potentially 2 electrons. If I add a 4th electron, it gets even more shielded because there might be more electrons getting in between it and the nucleus. So adding more electrons means that that next electron is going to be less attracted. That one's easy. Alternatively, if we're considering 2 different systems, one that has 3 protons and one that has 4 protons with identical amounts of electrons, isoelectronic systems, you would expect that the one that has the higher positive charge in the nucleus is going to be more attractive, period, right? So if I hold the number of electrons constant and I say, okay, here's an element that has 3 protons, here's one that has 4, which one's going to attract the electrons more? You're going to say the one that has more protons, right? Yes? Okay, good. So I got like half a yes, and I'm good enough to move on with that, but oh well. So all things being equal, if you hold the nucleus constant and you look at more electrons, those electrons are going to be less attractive. They're going to be less compelled to be around the nucleus, to stick with that nucleus. And the more protons you have in a nucleus, the more electrons are going to be compelled to be there, right? Just like if you have a sports bar, the more people that are packed around those flat screens, the more cramped it's going to be in there, the less people are going to want to hang around. And the more flat screens you have, the more people are actually going to want to be there, right? So flat screens are like protons. The number of people in the sports bar are like electrons. So going back to our sports bar analogy, kind of, we asked that horrible question. Oh, man. Let's do it this way. So we were concerned with something like the following. We were concerned about which one of these is going to be have more attraction between the outermost electrons, the ones that inevitably define its chemistry, how big it is. The highest energy electrons kind of determine what's going on with the element or with the ion. How attracted these are to the nucleus if we have 3 electrons and 3 protons versus 4 electrons and 4 protons. Which one's going to be bigger? Which one's going to be smaller? And as it turns out, this is a fairly complicated question. And the way it works is, if you are in a shell of electrons, like if you're in a valence shell, like if you're in one of those periods of the periodic table, and you're just adding an extra proton and electron as you're moving across a period, then the answer is you actually get smaller as you add both a proton and an electron. If you are moving up and down, like if you're moving down a column or down a group of the periodic table, then the size gets bigger. You're actually filling up a new set of orbitals. Each set of orbital with a principal quantum number has a much bigger size than the previous orbital that corresponded to it. So if we're going from something that's filling up a 2s with one additional electron and you're adding another proton and electron to completely fill that 2s orbital, this one's actually going to be smaller. And the reason why it's smaller is because that additional electron doesn't completely shield the additional proton. So as it turns out, having in the same sports bar with you, having an additional flat screen that has one person watching it is of some value to you. If you're an electron and you're thinking, like if you're an electron and somebody adds an additional electron and an additional proton, then as long as you're still on that same orbital, having that additional proton is better for you. You'll be attracted a little bit more to the nucleus, because sometimes that electron is not going to be shielding you. That new electron might be on the other side of the proton of the nucleus, and so some of that extra positive charge will be felt by you. The electron doesn't completely shield it. Okay? So, alternatively, let's see if I can get a periodic table again. So, alternatively, if you are going from something like neon to sodium, the size of sodium is going to be a lot bigger than the size of neon, because you had to add like the next electron that you add is going to be in the next shell of electrons, the next valence set. So this next shell that you would have to add on is going to be so much larger that sodium is going to be way bigger than neon. Okay, so for periodic trends, I've tried to build this intuition about you thinking about how a electron is attracted to the nucleus. You should be thinking about that outermost electron and how attracted it is to the nucleus. And then we can use this to build out all the periodic trends. And there are quite a few of them. So let's go through them. One is ionization energy. Ionization energy is the amount of energy that's required to kick an electron completely out of the atomic system. So if you had like a gas particle of sulfur, and I don't know how you get sulfur in the gas phase, and frankly I'm scared to think about it. It's probably not a good place to be if that's the case. If you have sulfur in the gas phase, it's going to take some energy to remove its outermost electron from the orbital and just have it release that electron into space or into the rest of the system. To do that, you're going to have to overcome the attractive force between that electron and the sulfur nucleus. Let's think about this: sulfur versus oxygen. So oxygen, if you had the ionization of energy of oxygen, that's the amount of energy it takes to kick the electron out of the atomic system, the outermost, highest energy electron, out of the atomic system. And that ionization energy is going to have to overcome the attractive force between the oxygen nucleus and its outermost electron. Now, the question is, will the oxygen outermost electron be more attracted to the oxygen nucleus than the sulfur outermost electron is attracted to the sulfur nucleus? And the answer to this is that the oxygen outermost electron is going to be more attracted to the nucleus. It's going to take more energy to overcome that attraction. So oxygen is going to have a higher ionization energy than sulfur. Why? Well, because sulfur's outermost electrons are in orbitals that are much further from the nucleus. So if you look at that probability function for sulfur's p orbitals, those are going to be bigger p orbitals than oxygen's p orbitals, and these are the orbitals that the highest energy electrons are in either case. So these electrons are going to be further away from the sulfur nucleus on average, and they are going to end up being less attractive because they're further away. So you could think of that as being a rationalizing reason for it. It's also been experimentally determined that this is the case. So ionization energies get larger as you go up a group. So it takes more energy as you go up. It takes less energy as you go down. Okay. How about left and right? So an oxygen versus a lithium. I could ask you guys this without having given you the lecture, and if I ask the right questions, you get the right answer. So tell me, guys, oxygen versus lithium. Which one's a metal? Lithium is a metal. Which one's a nonmetal? Oxygen. Which one tends to give up electrons when it's involved in ionic bonding? Lithium, the metal. Which one tends to pick up electrons when it's involved in ionic bonding? Oxygen, the nonmetal. Which one is it going to be harder to pry electrons away from? Oxygen, the nonmetal. Which one is it going to be easier to pry electrons away from? Lithium, the metal. Suddenly, your knowledge of chemistry and reactivity is helping you figure out more basic things. So yes, lithium has a lower ionization energy than oxygen does. How can I justify this in another way? I can say that, well, every additional proton and electron that you add to a system, or that you conceive of being added to a system, the difference between going from like lithium to beryllium, for example, every time there's an additional electron and proton, the electrons are going to be held a little bit more tightly. They're going to be more attracted, like that outermost electron is going to be more attracted to the nucleus because that extra proton is only partially shielded by the extra electron. Right? That electron is not always going to be in between, like the other electrons are not always going to be in between the nucleus and the outermost electron. Sometimes they will be elsewhere on the other side of the nucleus. So, or alternatively, that outermost electron, because the probability orbital, sometimes it's inside the other orbitals. So for that reason, it's only partially shielded, not completely shielded. So every additional proton electron that you add to a system, or that you conceivably add to a system when you move from left to right in the periodic table, that means that you're going to have a smaller atomic system. It'll have a smaller atomic radius because things are held more closely together. They're more attracted to the nucleus. Tell me about the ionization energy. Is lithium going to have a higher ionization energy, or is beryllium going to have a higher ionization energy that corresponds to having to pry electrons away from a nucleus that they are more closely bound to? The outermost electron in lithium is going to be more weakly held to the lithium nucleus than the outermost electron in beryllium, because beryllium has one more electron and one more proton, and that one more electron is only going to partially shield the extra proton. So whatever the outermost electron sees with the nucleus and the inner electrons, it's going to be a higher number than lithium. So what is the higher ionization energy, lithium or beryllium? Any guesses? Beryllium, right? Okay. More attraction here. Extra proton, extra electron. That means you still see a little bit of that proton sometimes, so there's more attraction. So more attraction means higher ionization energy. It takes more energy to pry that electron away. So as you move from left to right, you have higher ionization energies. It takes more energy to pry an electron away from fluorine than it does to pry an electron away from lithium. You also have smaller atomic radii. This is something that students have a hard time with, and I probably did too when I was learning it, because it's counterintuitive. You are adding a proton and an electron, and the system gets smaller. It should not be counterintuitive, because as I told you a long time ago, the world, even things that seem solid, are mostly empty space, and even inside of atoms it's mostly empty space. And it's not like these electrons are bumping into each other constantly. In fact, they hardly ever do that. In reality, they're mostly empty space. You can almost think of them as like little points. They're that small. And because of that, what's really happening here, what's dictating the size of these atomic systems, is how much the outermost electrons are attracted to the nucleus. So I told you that one more electron and one more proton gives you a little bit more attraction. So every time you go from one to the left to one to the right, you're going one more electron, one more proton. And that means that you get more and more attraction as you go. So ionization energy gets smaller as you go down, and it gets bigger as you go to the right. All right, let's introduce some more periodic trends. Atomic size, the radius of the atom. More attraction means that the electron will be held more closely to the nucleus. So it is going to be opposite ionization energy, right? So more attractive force between the electron and the nucleus. You have more attractive force as you go up and as you go to the right. So you would expect that you get smaller and smaller atoms as you go up and to the right. Yes? Same phenomenon, different manifestations of the same phenomenon. Okay. And there's more. So that's ionization energy. Hooray. You know, it's just releasing an electron. Here's a picture of it. Oh, here's atomic size. So, I mean, this is counterintuitive. You're adding a proton, you're adding an electron, and it gets smaller as you go to the right of the period. Just deal with it. Atomic size does increase as you go down, again, because you're adding bigger and bigger orbitals to the set of orbitals that electrons are populated in. So like a 1s orbital is way smaller than a 2s orbital, way smaller than a 3s orbital, way smaller than the 4s, 5s, etc. And this is pretty much a pretty darn good trend. It holds up pretty well. There's a couple exceptions, but I don't even know if they're exceptions. They're like there's a couple mitigating factors that we'll not talk about called the lanthanide contraction, but whatever. Okay, so yeah, we can do this one. So which one's going to be a larger atom and why? So we have sodium versus chlorine. Yay. So here's chlorine, here's sodium. Are they in the same period? Yeah, they're in the same row. Okay. So we're talking about the same orbitals being filled up here, but different numbers of protons and electrons. Do atoms get smaller as you add one proton and one electron? Yes, right? So going from sodium to magnesium, it gets smaller because that extra proton charge is not completely shielded. So the outermost electron of sodium sees like X charge in that nucleus. Magnesium sees X plus a little bit. X plus like 0.3 or something, like a fraction of that extra proton. So that electron that we've added to magnesium is going to be more tightly bound to the nucleus because it sees a little bit more positive charge. So as you go from left to right, you would have a smaller atom. So chlorine is going to be smaller than sodium. And the larger one will be sodium. Lithium versus cesium, let's check that out. Here's lithium, here's cesium. Are they in the same group? Yes. Which one's going to be bigger? Cesium, because it has electrons occupying much, much larger orbitals. So cesium has an electron in the 6s orbital. That's the highest energy orbital and also the biggest orbital. And lithium has its outermost electron in the 2s orbital. So cesium is going to be much, much bigger. Arrange oxygen, fluorine, and sulfur according to increasing ionization energy. So increasing ionization energy means more energy is needed to remove an electron from the atom. That means we're looking for things of increasing attraction between the electrons and the nucleus. So it was sulfur, oxygen, fluorine. So increasing attraction means that we're going to want to see things that are higher in the periodic table and to the right of the periodic table. Higher because we're going from things with bigger orbitals to smaller orbitals that are closer to the nucleus. And we want to go to the right because to the right we have things that have an additional electron and proton, and the additional electron does not completely shield the additional proton. So we look for things that are more that way, diagonally up and to the right. So that's fluorine. That's going to be the most attractive nucleus for an outermost electron, and it's going to have the highest ionization energy, then oxygen, then sulfur. And that's what you see. You see that sulfur is the least, then oxygen, then fluorine. All right. Which of these elements has the smallest ionization energy? Lithium, beryllium, cesium, or potassium, rubidium. Let's go check it out. Yeah, so the least ionization energy is going to be one that's like the lowest in that column. They're all in that column. Let's take a look. Cesium. So that's going to be the lowest one in the column. All the other ones like lithium or potassium, they're higher up. So they have orbitals that are smaller, and that means that the electron's going to be closer to the nucleus. And cesium has something in the, or an outermost electron in the 6s orbital, so therefore it has the furthest away electron. It has the least attractive force to the nucleus. So it's going to have the lowest ionization energy. And there's yet another periodic trend called electronegativity. Electronegativity is the ability of a nucleus to attract an electron when it's involved in bonding. So if you have a covalent bond between two nuclei, the electronegativity will dictate which one of those two nuclei will have more of the electrons in the sharing process. So just like in real life, you can have sharing, but sometimes that sharing can be unequal. And the more electronegative element will tend to hog the electrons in the sharing of electrons. So electronegativity is kind of like a consequence of how attractive that nucleus is to valence electrons or to bonding electrons, electrons that are outermost or higher energy. So this is going to be a lot like ionization energy. The more attractive that nucleus is to high energy electrons, the higher the electronegativity. So electronegativity also gets higher, gets bigger as you go up and to the right. So just like you can think about ionization energy as being the attractiveness of a nucleus to the outermost electrons, you can think about electronegativity as being the attractiveness of a nucleus to bonding electrons. And it has the same periodic trend direction up and to the right.